Welcome back to The Explainer. Now, when you look at a massive cargo vessel or a passenger ship, your eyes naturally go straight to those towering superstructures and the vast decks. But the true engineering marvel, the structure that literally keeps the vessel safe and afloat, well, that lies entirely hidden beneath the waves. Today, we're diving into an absolutely brilliant piece of engineering that solves multiple massive problems all at once.
So picture this. It's the ultimate nightmare scenario for any ship, running aground. Imagine a massive vessel striking a submerged reef. The sheer force and the astronomical weight pressing down on that one localized point of the hull, it's almost unimaginable. Common sense tells us that tearing a hole in the bottom of a boat equals catastrophic flooding, right? Game over. Yet, modern ships can suffer severe lower hull damage and still safely make it to port. Which begs the question, why doesn't a grounded ship always sink? Well, the secret to a ship's survival is hidden just below the waterline. The answer is a brilliant macro solution known as the double bottom. Historically, ships were built with just a single layer of steel separating the ocean from the cargo. But over the early 20th century, naval architects developed the ultimate insurance policy. They created an ingenious structural barrier designed specifically to contain damage and prevent catastrophic flooding.
Let's look at exactly how that insurance policy works. In a traditional single-bottom ship, if the vessel strikes a rock and suffers even a minor hull breach, the ocean just pours directly into the main cargo hold. The cargo is ruined, buoyancy is lost, and the ship sinks. It's that simple. But in a double-bottom ship, if the outer hull gets torn open, the flooding is completely contained within that lower boundary. The inner bottom remains intact, the cargo hold stays bone dry, and the ship survives.
Okay, so what actually is this space? The double bottom is essentially a continuous box structure that runs along the entire length of the ship's bottom. It's bounded by the outer shell plating, which is the part touching the sea, and the inner bottom plating, sometimes called the tank top, directly above it. But here's the crucial part. This isn't just one giant empty cavern. The space is heavily subdivided into individual, watertight compartments. So if one section of the hull is compromised, the flooding is strictly restricted to just that localized area.
Now you might be thinking, dedicating all this volume strictly for emergency protection seems like a huge waste of highly valuable space. But ship designers are incredibly efficient. This space cleverly doubles as vital storage. To put that into perspective, the volume is utilized roughly like this. 40% is for ballast water to maintain stability, 35% holds heavy fuel oil for those massive engines, 15% stores fresh water, and the remaining 10% is the structural steel itself. By keeping all these heavy liquids low in the ship, it massively improves the vessel's overall stability.
All right, moving on to Section 1, the egg box structure, also known as the micro solution.
So how do you actually build a hollow steel box that's strong enough to support thousands of tons of cargo pressing down while simultaneously resisting the immense pressure of the ocean pushing up? The answer is a dense internal lattice. Between the outer shell and the inner bottom, you have what are called transverse floors. These are heavy vertical steel plates running across the width of the vessel. Intersecting them are longitudinal girders that run along the length of the ship. They physically intersect at exact right angles to form a continuous cellular grid.
If you were to slice the top off this structure and look straight down, it looks exactly like a cardboard egg carton, which is exactly why it's famously referred to as the egg box. But why use this specific geometry? Well, it's because this rectangular cellular grid is extraordinarily stiff and strong. Think about stepping on a single flat piece of cardboard. It crushes instantly, right? But if you step on a vertically intersecting cardboard egg carton, it easily supports your weight. The egg box structure acts exactly the same way, distributing extreme point loads across a very large area so the ship doesn't buckle.
Let's dive into Section 2, Assembling the 3D Puzzle, which introduces the fabrication problem.
Understanding the theory of the egg box is one thing, but actually building it in the shipyard? That introduces an incredible fabrication problem. You obviously can't just push two solid pieces of steel through one another, so shipbuilders solve this with a brilliant slotted assembly technique. First, the transverse floor plates are laid out flat, and deep slots are precisely cut exactly where the girders need to cross. Next, the longitudinal girder plates are lowered down right through those openings. It fits together exactly like those cardboard dividers you find inside a wine box. It's literally a giant 3D puzzle.
And because of this slotted matrix design, something amazing happens. The entire egg box structure locks together mechanically. It becomes completely rigid and self-supporting before the welders even strike their first arc. Seriously, not a single weld has been made yet, but the structure is already holding its own shape. It's only after the entire grid is perfectly assembled and aligned that the welders come in to fuse all those intersecting joints, locking the whole shebang together permanently.
Which brings us to Section 3, the manhole problem, dealing with access and inspection.
Once this dense, interlocking grid is assembled and enclosed, it basically becomes a claustrophobic steel maze. Yet shipyard workers must be able to get inside every single one of these enclosed rectangular cells to weld, inspect, and do lifetime maintenance on the tanks. So how do you move around inside a sealed steel egg tartan? The solution is cutting circular or oval manholes directly into every single floor plate. But you can't just grab a torch and start hacking holes in the steel willy-nilly. That would completely ruin the structural integrity. The exact location and sizing of these manholes are structurally critical. They are precisely mapped out to provide access without compromising the immense strength of the egg box.
Bringing it all together, our source material brilliantly sums it up like this. The double bottom is a safety-critical egg box structure. It truly is a marvel of spatial efficiency and structural integrity. By cleverly utilizing those intersecting floors and girders that slot together, shipbuilders create a localized fortress. It provides absolutely essential buoyancy protection, seamlessly houses vital fluids, and creates the rigidly strong foundation upon which the rest of the colossal vessel is built.
So, we've seen how flat steel plates are transformed into incredibly strong 3D egg box subassemblies. But of course, a ship is much more than just its bottom. In the next phase of construction, these completed double-bottom units are combined with side shells, bulkheads, and decks to form massive multi-story blocks. Until we cover that next step, I'll leave you with this to ponder. When you see a massive cargo ship effortlessly gliding across the ocean, ask yourself, is it really the sheer volume of the ship that conquers the sea? Or is it the invisible, perfectly calculated geometry hidden beneath the waves? Thanks for exploring this with us today, and keep learning.